In the last part of the lectures that discuss stress, we are going to look at traditional stress-based failure criteria. So in general, I have a state of stress that's described by a matrix, and I'm looking for a measure that would tell me a measure of the stress matrix, and I'm wondering if this measure is critical or not. I'm wondering if this stress state represents a critical stress state where the material is about to fail or not. So in general, the stress-based failure criteria could be dependent on the orientation of the plane that I would like to check. So for example, if I have this state of stress that's described by a stress matrix sigma on 1 and everything else is 0, and let's say I have a really weak plane, this weak plane, and I'm using some bolts, for example, or some shear studs. Now this material will never, or those shear studs will never fail, because the stress on this plane is always 0. The sigma 1, 2 is always 0. So this, the shear of these studs is not expected, and so it's really dependent on the orientation. Even if I increase sigma 1 as much as I want, and if I'm just worried about the failure of this shear plane, this will not happen. On the other hand, if I apply sigma on 1, where the stress state is made out of sigma on 1, 0, 0, and I'm worried about this particular plane, and it's a weak plane, and I'm using some shear studs to protect this plane from shearing. Now the shear on this plane, if you actually calculate the shear on this plane, first you have to calculate n, and then calculate Tn, which is equal to sigma transpose n, and then you calculate the shear stress. So knowing the shear stress on this plane, which is not equal to 0 in this case, because the forces are applied in this direction, so there is a component on this direction. So the shear stress on this plane, I have to compare it to the critical shear stress, and by comparing the value of the shear stress at this plane to the critical shear stress, I'm able to know whether this material will fail or not, or the shear studs will fail or not. So first, we're going to present an example that details or discusses stress-based failure criteria in a general continuum. And we're going to start with a very general material, a wood beam. And we're assuming that a wood beam with a general orientation can withstand a maximum tensile stress of 25 MPa in the direction of the fibers U fibers 110. So I have a wood beam, and in the direction of the fibers, the maximum tensile stress is equal to 25 MPa. And in a maximum tensile stress of 10 MPa on the surface with the normal equal to U negative 110. So in this direction, on a plane with this direction, the maximum tensile stress is equal to 10 MPa. And on the same surface, the maximum shear stress is equal to 10 MPa, a maximum shear stress of 10 MPa on the surface with the normal U negative 110. So maximum shear stress is equal to 10 MPa. Now inside the beam, I put it in its carrying load, and inside this beam I calculate the state of stress given the loads, and the state of stress given the loads is represented by this stress matrix: 25, 10, 10, 10, 10, negative 3, 10, negative 3, 5 units of MPa. Now, given these failure criteria, will the stress matrix, will the beam fail or not? So the first thing is the first criteria: a beam will fail if the maximum tensile stress in the direction of the fibers is reached. So in the direction of the fibers, U fibers is given by 1, 1, 0. Now to calculate a stress on a plane, I have to find the normal to this plane. So this is U fibers, this is the plane. So N, the normal to the plane, is equal to the unit normal, so 1 divided by norm U, multiplied by U fibers, which is basically 1 divided by root 2, 1, 1, 0. So this is the unit normal vector. The traction vector, which is the force per unit area on this plane, is equal to sigma N fibers. The stress matrix is given by 25, 10, 10, 10, 10, negative 3, 10, negative 3, 5, multiplied by 1 over root 2, 1, 1, 0. When you multiply these two together, you get a force per unit area: 24.75, 14.14, 14.14 MPa. So given the normal stress, then, is the dot product between this force per unit area and the normal vector, which will be equal to 1 over root 2, 1, 1, 0, multiplied by 24.75, or the dot product between the two vectors, 14.14. 14.14, and this will be equal to 27.5 MPa, which is actually greater than 25 MPa, which is what is allowed in the problem. So the tensile stress of 25 MPa in the direction of the U fibers has been exceeded, which means the material has failed or is about to fail. Because we have applied stress that's more than what the material can take in this direction. Now for the other plane, for plane with normal U equal 1, negative 1, 0, the first thing I have to do is find the unit vector. In this case, N will be equal to 1 over root 2, 1, negative 1, 0. I just normalized the vector, found the vector whose norm equal to 1. For this plane, the normal stress, which is the stress perpendicular to the plane, is equal to the dot product between Tn and N, and Tn is equal to sigma transpose N dot N. If you take that dot product, if you take that dot product, the value will be equal to 7.5 MPa. If we do this calculation, which is less than the given 10 MPa for the maximum normal stress on this plane. The shear stress, which is the norm of the remaining vector, Tn minus sigma n in the direction of n. This value will be given by 11.86 MPa, which is greater than 10 MPa that's given in the problem. So it will fail due to shearing on the plane perpendicular to n. Okay, so this is how to check whether material will fail or not, according to the orientation of the stress and according to the plane that is under consideration. We look at the plane, we know what the maximum normal stress is on this plane, the maximum shear stress on this plane, and knowing what the actual stress is, we can find the actual normal stress and the actual shear stress, compare them with the maximum values, and know whether the material will fail or not. Now, for isotropic materials like concrete and steel, we might not need to look at an orientation and just look at one number from the from the stress matrix, and based on one number from the stress matrix we can find whether the material will fail or not. So for isotropic materials, we can extract one number from the stress matrix and use it to indicate whether material has failed or not. And the first number that we can extract is the maximum shear stress. And this maximum shear stress failure criteria is called the Tresca failure criterion. The Tresca failure criterion basically says the following. Look at your stress matrix, find the maximum shear stress, which is the maximum between sigma 1 minus sigma 2 over 2, or sigma 1 minus sigma 3 over 2, or sigma 2 minus sigma 3 over 2, the maximum difference between the principal stresses, and compare the number that you get with a value that's dependent on the material, a material dependent property. And if the actual stress reached that value, then your material is about to fail. First, this failure criterion is invariant. It's independent of the coordinate system. Why? Because your principal stresses are independent of coordinate system. The values are independent of coordinate system. Calibration. How do you calibrate? So let's say I give you a material and say this material is going to fail according to the Tresca failure criterion. Well, what you do is you take it to the lab and you pull it with sigma y until it fails at sigma y. So when material fails, you write that sigma in this case was equal to sigma y 0, 0. So the material failed, and the maximum shear stress in this case was equal to the maximum difference, which is sigma y minus 0 divided by 2. And this is the calibration to find your tau max. So you take it to the lab to find your tau max, and example, if it fails at sigma y equal 100 MPa, your tau max in this case is equal to 50 MPa. Now what does this failure criteria predict in a case of a pure hydrostatic stress? Let's bring a piece of metal. Let's bring a piece of metal and put it in the ocean under an extreme, in the deep parts of the ocean under extreme hydrostatic pressure, where the stress in this case is equal to P 0, 0, 0 P 0, 0, 0 P. In this case, maximum shear stress is equal to P minus P divided by 2 is equal to 0. So this material will never fail under a hydrostatic state of stress and according to Tresca. So Tresca predicts that this material, you can put as much P as you want, this material will never fail because the shear stress on this material is always equal to 0. So let's look at an example. A material or a metal that follows the Tresca yield criterion yields in a uniaxial state of stress when the uniaxial stress reaches 200 MPa. Basically, we took it to the lab, we applied a uniaxial state of stress, and it failed at 200 MPa. I'm going to use this to calibrate my material to find tau max. So 200 minus 0 divided by 2 is equal to tau max, equal 100 MPa. In the lab. In the state of stress or under the state of stress, sigma is equal to 25, 40, 40, 20, 30, 0, 30, 20, 0. What is the maximum sigma ij? Find the eigenvalue, eigensystem of sigma. The eigenvalues are one of those numbers, 71.7, negative 28.5. 28.5, 21.8, and the maximum shear stress will be equal to the maximum difference. The maximum difference is given by 71.7 minus 28.5 divided by 2, which is equal to 50.1 MPa. Okay, well, how does this compare to what the material can hold? The material can hold tau maximum, which from the lab was equal to 100 MPa. Therefore, the metal is safe. Under Tresca, yield, or according to Tresca, yield criteria or criterion. So let's visualize this Tresca yield criterion using a graph. And basically what I want to write is, or what I want to visualize is this equation. I have an equation that says the maximum sigma 1 minus sigma 2, sigma 1 minus sigma 3, sigma 1 minus, or sigma 3 minus sigma 2 divided by 2 is equal to tau maximum. When will these values equal to be tau maximum? And let's say if sigma 3 is 0. When sigma 3 is 0, you'll find that I can draw a line or a graph that tells me at which point will material fail. Inside this graph, the material is safe. So let's try to understand this graph. This point is represented by sigma 1 equal to 2 tau max and sigma 2 equals 0. Indeed, if sigma 1 is equal to 2 tau max and sigma 2 is 0, then the maximum of this will be equal to tau max. Any value here or any point here will represent a case at which the material is going to fail. So this line is the critical zone. Inside, it's the safe zone where the material is less than where the maximum sigma 1 minus sigma 2 and sigma 1 minus sigma 3 and sigma 3 minus sigma 2 is less than tau max. So inside is the safe zone where the values are less than tau max. On the line, it gives me the critical zone where the material is about to fail. The next failure criterion is the von Mises yield criterion, and the von Mises yield criterion again is independent of the coordinate system, independent of the orientation. It basically says find your stress matrix, find the von Mises stress. If the von Mises stress reaches a critical value that's dependent on your material, then the material is about to yield or is about to fail. Again, this is invariant, independent of coordinate system and orientation. And again, to calibrate it, you take a piece of metal, take it to the lab, find your yield stress, and calculate your von Mises stress for calibration. This will be equal to sigma y equal to sigma max. So your calibration states that your critical value sigma max is just basically equal to your yield stress and tension. And similarly in the hydrostatic state of stress, so in a hydrostatic state of stress, so if I get a piece of metal and put it deep inside the ocean and apply P from all directions and no shear stresses, the von Mises stress yield criterion predicts that material will never fail. Not only this, it predicts failure also the von Mises stress predicts same failure pattern for sigma and negative sigma. If you take your stress and multiply it by negative, so you take any value of stress and you take the negative of that value, the von Mises stress will predict the same pattern. So again, a problem just to visualize this failure criterion. Again, I take a piece of metal and I tell you that it follows the von Mises yield criterion, and in the lab I tested it and I found that sigma yield is equal to 200 MPa. That's when the material started to fail or to show signs of failure. In this case, the von Mises stress, which is equal to the absolute value of sigma y, will be equal to 200. From this, I can calibrate my material, and this is equal to my sigma max. Now, in the current state of stress, or in the state of stress represented by sigma equal to 25, 40, 0, 40, 20, 30, 0, 30, 20, the von Mises stress, which is a huge equation, function of all the variables in the stress matrix, will give you a value of 86.75 MPa, which happens to be less than the value we found from the lab. Therefore, metal is safe under the von Mises stress criterion. So again, the last thing we want to discuss in the failure criterion is the graphical representation of the von Mises yield criterion when sigma 3 equal to 0. When sigma 3 equals 0, I would like to draw the equation that states von Mises stress, which in this case will be equal to sigma 1 minus sigma 2 squared plus sigma 1 squared plus sigma 2 squared divided by 2 in a coordinate system of the when sigma 1, sigma 2 and sigma 3 represent the principal stresses of the stress, and when sigma 3 is 0, this equation can be visualized using this ellipse. Any point here, when the values of sigma 1 and sigma 2 satisfy a point on this curve, this is critical value. It means that the material is about to fail. any point inside means that the von Mises stress is less than sigma max, which means material is safe, or state of stress is safe. So I'm not going to cover the other isotropic yield criteria, and I'm not going to cover the Morse circle for plane stress. You've studied Morse circle in previous courses. You can read this section if you would like to compare the Morse circle to what we've been studying in continuum mechanics. And the last section in this chapter, which is the stress chapter, is other measures of stress, which is basically what is the difference between engineering stress and true stress, which you will hear a lot about, especially when you look at the stress strain curves of metals. And basically these concepts originated when, in the past, when they take a piece of metal and take it to the lab and apply a force P and draw P versus delta, where delta is the displacement of this material. They would get a curve that looks like this. Then what they would do is, in the past, they would measure the area before the application of any force and the length L0 before the application of any force, and normalize the force by dividing it by A0, and normalize the length by dividing it by L0. So you get another curve that looks exactly similar to the above but different units, and this is called the engineering strain, and this traditionally is called the engineering stress. But what was found was, as P increases, area decreases, and the stress is in fact equal to P over A. It's equal to the force divided by the actual area, not A0, and thus they termed this value true stress. And since in metals we assume volume doesn't change, then we can relate AL, which is the current area, the current length, by the original area and the original length. And we can say that L divided by L0 is equal to L0 plus delta divided by L0, which is equal to, of course, this is equal to E0 over A. So E0 divided by A is equal to L over L0, and L, which is the length, is equal to L0 plus delta divided by L0. L0 divided by L0 is 1. Delta divided by L0 is your actual engineering strain. So I'm going to call this epsilon engineering. And so the true stress which is equal to sigma true, we call it designate sigma true, we divide P by A. This is equal to P divided by A naught multiplied by A naught divided by A, which is equal to sigma engineering multiplied by A naught over A, which happens to be 1 plus epsilon engineering. And we also introduce another measure of strain, which we will discuss later in the next chapter, which we call true strain, which is equal to epsilon true. Epsilon true is equal to, instead of delta over L naught, I'm going to take the logarithm Ln, the natural logarithm Ln of L over L naught, which is equal to ln of L over L naught, which is equal to 1 plus epsilon engineering. And so, given any stress strain curve, knowing the engineering stress strain curve, and can find what is referred to as the true stress strain curve, where this is the stress and this is versus the strain, and if this is in a uniaxial state, and this relationship is obtained by simply given the table of the stress versus strain, sigma engineering, epsilon engineering, given those values that make the curve, I can find sigma true, which is equal to sigma engineering multiplied by 1 plus epsilon engineering. So I can find the relationship between sigma true and epsilon true, which is equal to the natural logarithm of 1 plus epsilon engineering. And I can draw these curves, and you have an example in your notes, in your book, to show how to draw such relationship. So this is it for this chapter, for the chapter of stress. The last section is not covered in the undergraduate course. And in the next chapter, we're going to study the concepts of deformation and strain.